Welcome back to Physics 426. Um, we're talking about magnetic fields due to electric current right before spring break. Now we've had an extended spring break, so we're going to pick up. There was really only just one section left in chapter 29 that we needed to cover, so we were almost done with 29. So that's good. We were just a little bit ahead of where we needed to be, and so chapter 29 we had done most of it. We are now ready to start talking about solenoids. Okay, so refreshing your memory, the bulk of chapter 29 was an introduction of Ampere's law. So Ampere's law says you got a magnetic field, and so the magnetic field is going somewhere. Okay. And so if you were to take a path in the magnetic field, a closed path in the magnetic field, the integral around that closed path of B dot ds equals mu naught times the current. So that is Ampere's law. Okay. And so we did several examples of Ampere's law before the end of the in the spring break. So that gave us a first step. Okay, we'll do a couple more examples of that possibly as we go. But one example that we can do with this is using it to describe a solenoid. Now, what is a solenoid? A solenoid is basically a coil of wire. So you got current going into a coil. So you got a coil of wire, okay, and current goes to the coil, okay. And so we want to describe what's the magnetic field inside there, because if you look at it, this is a side view right here. For a top view, then what would happen is you would have current going around like that. Okay, so current's going like that and kind of going around, in that direction right there. So using the right hand rule, curling your hand in the direction that the um, the coil is going, we see that the magnetic field has to be going into the screen right there in that fashion. And so magnetic field is in there. Okay, so it's going downwards everywhere in there. Okay, and you can also see that, if you look at this and take kind of a cross section of it as to what's going on, then each wire, and so each of the little circles corresponds to a wire right there. So each wire has magnetic field that is coming at you. So that means the magnetic field around each wire is going to be this way. So that means magnetic field down here, if you imagine in here a spot right there, the magnetic field to this one over here is like that. The magnetic field due to this one over here is like that. And so they add up going down. So the magnetic field inside the solenoid is always going down. Okay. So that's going to be our clue. So inside the solenoid, so again we got the current going around like this, and magnetic field's always going down inside the solenoid. And so if we imagine an Amperian loop, okay, so integral B dot ds equals mu naught I. And so what we're going to do is we're going to imagine a loop that looks like that. Okay. And so I'm going to integrate down, across, up, and that way in my loop. Okay. And so that means my integral now becomes a little more complicated. It's integral B dot ds on the left-hand side plus integral B dot ds on the bottom plus integral B dot ds on the right-hand side plus integral B dot ds on the top is equal to mu naught I. Okay. Now, integral B dot ds right here. Okay. In the middle of the solenoid, in the center of the solenoid up here, then if we're going downwards in the solenoid, that's the direction of the magnetic field, so the dot product goes away. And so if I just say the height of this thing is h, then that's just going to be b times h. Along the bottom, we would imagine on the outside of this thing, the magnetic field is going down, the magnetic field on the outside is going up. So that means the dot product is perpendicular, they're orthogonal. And so that goes away. So that's 0. Okay. Likewise, on the top, that's also 0. Now, what about on the right-hand side over here? If I take a limit as that goes to infinity, how strong is the magnetic field infinitely far away? Well, that's going to be 0. So the b right here is going to be 0, which makes the integral 0. So that means the magnetic field is just going to be b times h equals mu naught I. So that's the result of doing Ampere's law for that particular loop. Okay, so now the question is, we got b times h equals mu naught I. Okay, so b times h equals mu naught I. Well, I is really not just the current in one loop because you get more than one loop. So it would depend on how many loops were in there. So that's going to be n times I because we have n loops. N is going to be an integer, just the number of loops. So now my equation is b times h equals mu naught times n times I. Okay, so b equals mu naught n over h times I. So that's the magnetic field inside of that solenoid. And so your book would then rewrite that. The book rewrites that and says the magnetic field in a solenoid is equal to mu naught n over L times I, where L is now the length of the solenoid. N is the number of turns the solenoid, L is the length. Now, assuming the solenoid is actually a symmetric sort of winding and all the turns equally spaced, that ratio N over L is the same no matter how long the solenoid is. And so we make a new definition. N, little n, equals the number of loops over the length of the solenoid. And so there you have an expression for the magnetic field in a solenoid. It's equal to mu naught times the little n, which is like how tightly wound the solenoid is, the number of turns per length, times the current in the solenoid. Now, if you think about it, we did our Amperian loop here. Okay, so we said the magnetic field is perpendicular at the top and the bottom, so we didn't have to worry about that in the integral. We said really far away over here, magnetic field's really weak, so we didn't have to worry about that. So what about in the middle here? What if I had moved this over a little bit? What would that have done? And the answer is nothing. That doesn't actually play a role in this. And so that would suggest that the magnetic field inside the solenoid is the same everywhere. So it's a constant. It's mu naught n times I, little n times I. So that's the magnetic field of a solenoid everywhere inside. So this is a way you get a constant magnetic field. You know, we had talked about how to get a constant electric field. A constant electric field you can get in a capacitor by having parallel plates. And so that would make the electric field constant in there. This is how you get a constant magnetic field, is you can make a solenoid. And so that's the basic theory behind solenoids.